This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good afternoon. So today we'll talk only about root locus, and in particular how to plot different root loci. So in the LMS, in the worksheet, you are given this really concise and nice summary of steps of sketching the root locus. So they are summarized in the lectures, but here it's a very sort of easy to use recipe, and it's a useful thing to have in the exam situation, right? So I urge you to have this handy when you are sketching your root locus. So what are the steps? So the first thing is to write characteristic equations so that the parameter of interest k appears as a multiplier. So you need to rewrite, so you may have a block diagram, right, complicated block diagram, and you will write what the denominator of the closed loop of the overall system is as a function of k. And then you would rewrite it in this form, 1 plus k times p equals 0. So this is the first step in plotting the root locus of a given system. Now, the next step is to find all the poles and zeros. So you want to rewrite the transfer function of p as a ratio of the product of s plus zeros, well, zi's, actually they're not zeros, they're minus zi's are zeros, and divided by product of s plus pj's, right? So this is the sort of important step because you want to identify all zeros and poles. So zeros in these representations are what? Minus zi's, right? And poles are? Minus pei's or pj's, yes. So then the next step is locate open loop poles and zeros of p in the S-plane with selected symbols. So crosses for poles and circles for zeros, right? Then we need to determine the number of separate loci. So the number would be the maximum between the number of poles and zeros. So you look at the m and n here. M is the number of zeros and n is the number of poles, and then you take the larger one. Now, often you would get a case where the number of poles is larger than the number of zeros, but that's not necessary, okay, in general. So then you need to note that the locus, every branch of the locus would begin at a cross, and it will end up in a circle or in an asymptote. It would follow an asymptote, right? So then you need to note that root locus is symmetric with respect to the real axis, right? Always you can just plot the upper part above the real axis and just mirror image it on the down part. So there's always this property, the root locus is always symmetric with respect to the real axis. So then you want to find the asymptote. So the branches of locus would, some branches would proceed to zeros at infinity along asymptotes. Now, asymptotes would intersect the real axis at this point, where this is the sum of all the poles. By the way, these minus pi's are all the poles, and this is all zeros, right? Sum of all zeros. So this means sum of all poles minus sum of all zeros divided by the relative degree, so n minus n, okay? N is the number of poles, m is the number of zeros. And the angles are given by this formula. I did give you examples of what the asymptotes look like for the relative degree 1, relative degree 2, 3, 4, etc. So, you just have to subdivide 360 degrees in equal parts. It's like dividing the pizza, 360 degrees into equal parts. How many parts? Well, that depends on the relative degree. So you take the relative degree and you will have exactly this number of asymptotes, right? And then you need to determine the points at which the locus crosses imaginary axis. You need to use Ralph Hurwitz criterion. So you will have a characteristic polynomial here expressed in terms of k, so coefficients you can get from here, characteristic polynomial. So if p is some polynomial b of s divided by a of s, then the characteristic polynomial is a of s plus k b of s. So you will have that coefficients in this characteristic polynomial will depend on k, right? And you have to write the Raud-Hurwitz table as a function of k. And then you look at the column, first column in the Raud-Hurwitz array. So if for all positive k's, the first column doesn't change sign, then we don't have crossings with the imaginary axis. If for some values of k, we have that some entries in the first column of the Raud-Hurwitz array are 0, then we will have crossings of the imaginary axis. Okay? And then what you need to do is you need to determine breakaway point on the real axis. So what you can do is you can find k as a function of s, find its derivative and set it to 0. This is one of the possible ways of finding the breakaway points. Basically, breakaway points are, if you're on a real axis, for instance, there are two branches traveling towards each other. At some point, they would meet. The point where they meet would give you multiple solutions. Then you have a pole with a multiplicity, 2. And then what you can do is you can look at the characteristic polynomial. You look at also derivative with respect to s of the characteristic polynomial. And any solution that solves both polynomials would give you breakaway points. So that's one way of doing it. We showed two ways of doing it. One is, sorry, I lost the mic. Another way is to write k as a function of s from the characteristic equation, find its derivative and set it to 0, and then solve that. You will get the same solutions. Then you need to determine so-called angles of departure from complex poles or arrivals at complex zeros. For this, you use the phase condition. We will see some examples on how to do that. And then finally, you need to complete the root locus. All right. So, by the way, you have a lot of solved examples that I will present in the workshops. We will work through some workshop sheets together. But we can maybe start by some really, really simple cases. So let's start with something very simple, and then it will be maybe easier to look at more complicated things. So I will start with things that, so this is workshop 5, right? Some very simple things. So suppose that your transfer function that you are looking at is 1 of s plus some c, where you are looking at 1 plus k, w of s equals 0. So c here can be just any real number. So we want to just plot a root locus for something like this. So what are the zeros of this transfer function? So there are no zeros. What are the poles? Minus c. But c can be positive or negative. So, right? So if c is negative, minus c is positive. Right? In any case, if we follow the rules for plotting, so first we rewrote everything in this form, right? Yeah? So now we want to denote where poles and zeros are. So where are the poles and zeros? I'll start now plotting the root locus. Well, if c is smaller than 0, then there would be one pole here. If c is greater than 0, then there will be one pole here. And if c is equal to 0, then there will be a pole here. Right? So suppose, we deal with this situation. Right? So now we need to determine what is the part of the real axis that belongs to root locus. How do we do that? So whatever is to the left of this guy, so this is the only pole now, right? So this would be part of the root locus. Now, my question to you, do we need to do anything else in this case? No, we don't. Because there is only one branch. How many branches? There are 0 zeros, there are no zeros, and there is one pole. So there would be one branch. So difference between 1 and 0 is 1. So there's one branch. And how many asymptotes would we have? Relative degree is 1. Well, there is one asymptote, and I already showed you that in that case the asymptote will tend towards negative infinity, right, along the real axis. So this is the root locus for this system. And note that depending on the constant c, the root locus might start from here if we have an unstable pole, open loop pole. It may start from here if we have that c is 0, so we have just an integrator. And then it may start from here when c is negative, in other words, sorry, when c is positive, in other words, the pole is negative, because pole is minus c. Pole is minus c, right? So this is minus c. And this is also minus c, but since c is negative, that's in the positive case, positive part of the real axis. So this is it. So for transfer functions that are first order, have only one pole, that's it. There's nothing else to do. All right. How about, so this is, let's say, first example. How about second example? Now, W of S is equal to, let's, S plus Z, and then S plus P. What would be the, where Z and P can be again any real numbers? I want to say if Z and P are both positive, we will have a stable 0 and a stable pole. If both are negative, we will have unstable 0 and unstable pole. All right. Let's consider different cases. What happens here, right? By the way, how many asymptotes would we have here? 0 asymptotes. There are no asymptotes. No asymptotes. How many branches do we have? We have maximum between number of poles and zeros. There's 1, 0, 1 pole. Maximum is 1. Right? 1, 1. Maximum is 1. So suppose, let's consider different cases. Suppose, let's say 0, so Z and P. Suppose that we consider this case. So Z is larger than 0, but it is smaller than P, right? So both of them are positive. So let's now do the first step in plotting the root locus. So where would be the 0 of this transfer function, open loop 0? It's minus Z. Since minus Z, well, Z is smaller than P, then 0 would be closer. This is minus Z, this is minus P. 0 is closer to the imaginary axis, right? So what would be the root locus in this case? Well, the root locus will start from pole, but it would converge to the 0. Because this part of real axis is not part of root locus. This part is, right? Because we are to the right of any point here, there is only one singularity, right? And here again, this is not part of root locus because to the right of this point, there is 1 pole, 1, 0, total 2. So it's an even number. So we don't have that this is like any point here is part of root locus. So this is the root locus. But note now, I assume that 0 is positive. What would happen if I assume that 0 is negative? So, sorry, if that Z is positive. What if Z was negative? Well, this point here would end up here. So what does that mean for stabilization for this system? High gain would do what to the system? It would destabilize the system. It would destabilize the system. What happens if we swapped pole and 0 here? So if I said, what happens now? So let's consider the next situation. So what happens if I assume that pole, so P is smaller than Z, and that's greater than 0. Sorry, all of them are greater. So then pole would be closer to the imaginary axis, right? So what is the root locus in this case? It's again this part of the real line, right? So this is the only branch. It starts from the open loop pole. It ends up in the open loop 0 for high gain. So let's compare these two diagrams. So if I look at the first one, and I think now about settling times. So settling times would be related to these sort of vertical lines that intersect the negative real axis at different points. So the further we are from the imaginary axis, the faster, the smaller the settling time, right? So basically what we can see here, as we increase the gain, in this case, the closed loop pole is traveling from this point to that point, and what happens to the settling time? It decreases. How about here? When we have pole is close to the imaginary axis, now we are traveling in a different direction. It increases. Yeah. So you are getting a hang of it, right? So some of the root loci are very simple to plot. Yeah. All right, let's look at more complicated examples. So I'll just say this is W5, 2. Suppose now that we consider a transfer function that looks like this. Let's do something a bit more sort of interesting. So suppose that W of S is 1 over S to power 4. What will we do here? Well, how many, so I'm looking at 1 plus k W of S equals 0, right? How many poles do we have? Open loop poles, 4. They are all at the origin, so I should, put really 4. So there are 4 at the origin, right? Now, what is the number of branches here? 4. We have no zeros, 0 zeros, 4 poles. Maximum of 4 and 0 is 4. There are 4 branches. Which parts of the real line belong to the root locus? Nothing. Because when we are traveling here, there are 0 poles plus zeros on the right. When we are here, there are 4 poles plus zeros on the right. So none of the points except for exactly the origin. But that's really for k equals 0. When k is equal to 0, then we are exactly at the origin. So what do you think root locus would look like in this case? Very good. Asymptotes. How many asymptotes do we have? 4. We need to divide 360 degrees into 4. The asymptotes look like this, right? So we are dividing things like that. But where would they intersect the real axis? Well, we need to look at the formula. So the formula for where they intersect the real axis is given here. It's the sum of poles minus sum of zeros divided by relative degree. What are all poles in this case? 0. What are zeros? There are no zeros. So this is really 0 divided by 4, which is 0. So all asymptotes intersect at the origin. So what the root locus looks like is like this. So what can we say about stability of this system, closed loop system? We can't stabilize it. For any value of constant k, we cannot stabilize, right? What would be the case if we have triple integrator instead of the quadruple integrator? If we had 1 over s to the power 3, would we be able to stabilize that guy? No? Okay, good. Because the asymptotes, one asymptote would be negative real axis, and 2 asymptotes would be going this way. They would still intersect the real axis at the origin, because this formula would still apply. 3 poles at the origin minus no zeros divided by 3 in this case, it still intersects at 0. So it still wouldn't stabilize. All right. So we are going from something like we are building up our knowledge of root locus. How about, so this is like a third simple example. Let's consider the fourth simple example. How about the case where W of S is 1 divided by you know, S plus some C to power 4. And I'm saying here, let's suppose that this C is positive. Can someone guess what the root locus would look like? Huh? It would be shifted, yes. It would be exactly like this guy, but the point of intersection of the real axis would be where? At minus C. Minus C. Why? Because there are 4 poles here, all of them are at minus C. I assume that C is strictly positive. When I plug in the formula for where asymptotes would intersect the real axis, here, this sum here is basically minus C, minus C, minus C, minus C 4 times, right? And then there are no zeros. And I divide by 4 because n is 4, m is 0. So basically, I still intersect at minus C. So the root locus would look like this. I have here minus C. What can we say now about how proportional control affects the behavior of the system? Large gain destabilizes, small gain stabilizes, but how does, so suppose that I say at this point where we cross imaginary axis, right, at this point where we cross imaginary axis, that would correspond to some critical gain, right? This would correspond to some critical gain. So what happens between 0, k, between 0 and k critical? What happens? What can we say about overshoot? What can we say about rise time? What can we say about settling time? Settling time increases, yes. Increases because if we are looking at how, so as we increase gain, the closed loop, these two poles corresponding to these 2 branches would be what? We would call them what? They are dominant poles. They are closer to the imaginary axis. So basically their location is most responsible to what will be happening to the overshoot, settling time, and rise time. So how do we decide what would be the overshoot? We consider, okay, for this value of gain, I will have poles basically lying here. Then I look at the line that connects that point to the origin, and I look at the angle that this line makes with the imaginary axis. Now, zeta, the damping factor, it's arc sine of this angle. So this, if this is a theta angle, then arc sine of this angle is zeta. So as we increase the gain, this line would do this, right? It would get closer and closer to the imaginary axis. So this angle would be smaller and smaller, and hence zeta would be smaller and smaller. So damping is smaller and smaller. And we saw that small damping means larger overshoot. What happens with the rise time? Rise time is related to those semicircles, right? So we still need to see, all right, for this value of gain, there are 2 poles, and then you need to look at the semicircle, you know, of radius omega n, right, that passes through these 2 points. So note that as we increase gain, the maximum radius of this semicircle would depend on the location of C. So by the way, this is 45 degrees, this is 45 degrees, right? So in the end, you know, the maximum, so I believe you would cross here at C, I believe, right? So we can check that. But you know, the maximum radius of the semicircle, you know, semicircle might look like this. So you need to plot this now carefully. But you know, you might get rise time to be the same for small gain and close to critical gain. They would be the same, roughly, right? So that's how you would analyze how, you know, the gain affects the behavior of the system. What would happen if C was negative? If C was negative, then this point here, so then we have here S minus, so minus C are all poles, but C is negative. So this point minus C is actually somewhere here. So everything is just shifted on the other side. In that case, what can we say about stability? Unstable, because two branches stay forever in the right half plane. Yeah? Okay. All right. So I wanted first to go through some simpler to plot examples, just so you get a handle, because we get into more complicated things. But this is, this is good. So what I'll do now is I will go through some of the solved examples. They are typed up, and we will just discuss the solutions as we go. I think it's also useful. It's just sometimes calculations are cumbersome, so rather than wasting time on calculating exact numbers, I can explain the steps. And you stop me, slow me down if it goes too fast. Okay? So let's go through tutorial questions now to go through a few. I hope that this was useful. So we have still half an hour. We can look through quite a few things. So here is the first question. It says, consider unity feedback shown in this figure where g of s is b of s over a of s for some polynomials a and b. So it says, given polynomials a and b, what does it mean for a point s0 to lie on the root locus of the feedback loop in terms of a and b? State this in your own words with relevant equations. So can someone tell me what does it mean for I pick a point S0 in a complex plane, and I'm asking you, is it on the root locus or not? That's the question. So what does it mean in terms of these equations, these A, B polynomials, etc.? How would you explain if a point is on the root locus or not? Anyone? So what we are dealing with here is the closed loop transfer function. So let's call this GCL. That's the closed loop transfer function. What is it for this unit feedback system? Is k times g of s over 1 plus k times g of s. Why is it plus? Because of this minus. So this is algebra of block diagrams for feedback connection. We've done that, right? So now we have to look at this guy here. So poles of the closed loop would be basically zeros of this polynomial, right? I mean, this is actually a rational function, but let's look at solutions of this. 1 plus kg of s equals 0 are basically points on which, points of where root locus is for some positive k. So if some point S0 is on the root locus, it means when I plug it into this equation has to hold for some k. So, but in terms of polynomials a and b, well, g is b over a. So this equation here is the same as a of s plus k b of s equals 0. So for a point to be on the root locus, it means that when I plug this point into this equation, there exists some k positive, so that when I plug in S0 into this equation, I can also find k so that this is identically equal to 0. The left-hand side is the same as right. That's what it means for a point to be on the root locus. Questions? All right. It says here, the second one is, let k be positive or no negative. Why must a point S0 on the root locus satisfy the phase condition that the phase of g at that point is 180 degrees? Why is that the case? Look at this equation here. So if I take this equation here, I can rewrite it. I can say that k times g of s is equal to -1. Right? From here, I get that. Yeah? So, but then, because what is on the left-hand side is exactly what's on the right-hand side, I can rewrite what's on the left-hand side as magnitude times, like the phase, right? The expression of the phase. And the same thing on the right-hand side. So what is the phase of -1? Yeah, in the complex plane, -1 is here. the phase is basically this. So that's 180 degrees or minus 180 degrees. Or we can take any number of rotations, right? But if I just say 180 degrees, that's fine. Yeah. So then, what is the phase of this thing here should be equal to this. So I can say that phase of that is the same as phase of that. But phase of that is 180 degrees. But what is the phase of this? Well, phase of all of this is phase of K plus phase of G of S. Why is this the case? Well, phase of the product of two things is the sum of the phases. What is the phase of K? Zero, because we assume that K is positive or non-negative. That's why, right? So that's why this is 0, and then we have that the phase of G of S is 180 degrees. Yeah. All right, what's the next question? So we are just going through these things quickly. It says, if a point S0 on the root locus satisfies this, what does this say about the gain if this gain is positive? Let's look again at this equation. So what this question is sort of asking you, for this thing here, I mean, I can rewrite this thing here as Kg of S is equal to minus 1, right? But then we used phase condition to write this, right? But what we didn't use is the gain condition. So what is the gain condition? Well, the gain of the left-hand side should be equal to the gain of the right-hand side, right? But I can rewrite this, I can divide by G of S, right? So I can say, from this same equation here, I can say that K is 1 over G of S with minus. And what is the magnitude? Well, the magnitude of the left-hand side should be the same as the magnitude of the right-hand side. Well, so K is positive. So norm of K is equal to K. That's the assumption, right? K is positive. So absolute value of K is the same as K. And then the magnitude of the other side, you just say 1 over G of S. So any point on the root locus should satisfy also this condition. Sorry. So if I give you a point on the root locus, right, on the S0, on the root locus, and I ask you what is the gain that corresponds to that point on the root locus, what you need to do is you need to find what S0 is, substitute it into the transfer function, find that you get a complex number, right? When you substitute complex number into rational function, right, transfer function, you get a complex number. You need to find the magnitude of that complex number and divide 1 over that number, magnitude. That's the gain corresponding to that point. Yeah? So just to go back to some of our examples, for instance, if I tell you, all right, what is the gain that corresponds to, let's say, point here, which is maybe minus K. So I shouldn't say K, minus W or something. So I pick a point and I say, what is the gain K corresponding to this point, right? Well, I have to substitute this W into the transfer function, right? So minus W, I just substitute it, so I will get what? Minus W plus Z minus W plus P. What is the magnitude of all of this? Everything is real. W is real, Z is real, there's no complex numbers here. So what is the magnitude? Well, the magnitude of all this is that, right? The magnitude of W is basically all of that, and that's a real number. So the gain corresponding to this is 1 over, all of this, minus W plus Z minus W plus P. That's it. That's the gain corresponding to that point. Is that clear? I don't see nodding. I see one person nodding, another tentative nod. Smiles. If I tell you what is the gain that corresponds to this location of closed loop poles? What is the gain that corresponds to this location of closed loop poles? So you pick that. So I say this is the location of the closed loop pole. That's a point on the root locus. Every point on the root locus, every point on the root locus corresponds to a certain gain, right? So I pick this point on the root locus. I say, what's the gain corresponding to this point? You can calculate it using that formula. Yeah? So just plug in the complex number that you picked, plug it into the transfer function. You get a complex number. You are evaluating transfer function at a particular complex number. Find its magnitude. You get the magnitude of a complex number. 1 over that, that's the gain. You get that from the magnitude condition of the root locus. All right. This is interesting. So suppose now that k is negative or non-positive. So what condition must, what phase condition should this guy satisfy for S0 to be on the root locus in the feedback loop? Explain. So how do you think you would address this? So now k is negative. So note, we have to go back to this situation. So still, we have that this equation holds. K times G is equal to -1, this still holds. The only thing is now K is negative, right? So still phase of the left-hand side and right-hand side should be the same. So this step here is still true. Phase of K times G should be equal to phase of -1. Phase of -1 is 180 degrees. But now when I split these phases, phase of this thing is phase of K plus phase of G. But then now phase of K is no longer 0, it's what? 180 degrees. So I would have 180 degrees and this 180 degrees would cancel, and then the phase of G for those points to be on the root locus is 0. It's no longer 180 degrees. So this is sometimes called negative root locus. Sometimes you want to plot this thing. Right? So K is negative and you will be applying different phase rule. Yeah? For positive root locus, phase rule is that the phase of G on the root locus should be 180 degrees. If it was negative root locus, the condition would be the phase of G should be 0. All right. So here's an interesting one. So it says an armature controlled DC motor with negligible armature is given here by this transfer function, and you're asked to use the controller with this transfer function, S plus 0.5 divided by S plus 6. So you have now that D of S is given by that, and G of S is given by that. So what's interesting about this situation? So what is the characteristic, what's the equation we need to consider in this case? Well, we still need to, so what's the closed loop transfer function? So I should probably say, well, D of S, the right way to think about this is that D of S is really K times all of this, because I'm trying to plot things with K in front, right? So there will be some parameters still that I would want to play with. So it will be, so the equation that we will be looking at in the end is 1 plus K ds gs equals 0. Now what's interesting about this is, note that there is a 0 at minus 0.5 in the controller, and then there is a pole at minus 0.5 in the plant. What do you think would happen in this case with the root locus? You will have pole 0 cancellation. So what you would need to do is the following. What are the poles and zeros of this whole thing? So you have 1 plus, I would just write it out completely. So K S plus 0.5 times, let's say, 4, and then you have here S plus 0.5, S plus 6. Right. That's the thing we need to consider. Now we still need to look at zeros and poles. So there is one zero and there are two poles of the open loop transfer function. So when we enter everything into complex plane, well, there is a pole at minus 0.5, but then there is a zero at the same spot, right? And then I also have here S that I forgot to put in, yeah. So where is the other pole? The other pole is at 0, and the third pole is at minus 6. So I would say here minus 6. So this is the first part of plotting. Like that's how we do it. First we plot where all the poles and zeros are. So what are the parts of the real line that belong to the root locus? So this part definitely yes. How about this part? Yes, because I do have to count both pole and zero here, right? How about this part? No. All right, very good. What is the relative degree in this case? 2. How many asymptotes? 2. So what would the asymptotes look like? They are just like a vertical lines. One is 90 degrees, one is 270 degrees. The two branches, right? Where would the asymptotes intersect the real axis? You remember the sigma, where asymptotes intersect the real axis, is sum of poles minus sum of zeros divided by n minus m, which is the relative degree. So what is the sum of poles? Well, one pole is 0, one pole is minus 0.5, so I should say 0 minus 0.5, then minus 6, right? And then minus, I have here minus 0.5, because that's the 0 corresponding to this part. Everyone follows? Divided by what? Sorry, not 4, 2. Yep. So what is that? So this 0.5 and this 0.5 would cancel. We have just minus 6 divided by 2. Yeah? What is that? That's minus 3, right? So at minus 3, this is my point sigma, and my asymptotes would look like this, because it's relative degree 2. So what do you think the root locus would look like? Do you think that things would, you know, be exactly like this branch going this way and then splitting this way, or something else? In this case, that's what you get. So how you can see that is you could look at where is the breakaway point. So the question is, would these two branches sort of travel, and then meet right in the middle? And in that case, they would follow the asymptotes, or would the breakaway point be here or here? In this case, it's interesting because we have this pole zero cancellation. You can also like almost ignore this thing here. So what would be the breakaway point? This would be exactly like what we did in the lectures. One of the first root loci we did was one pole at 0 and one at negative point. The asymptote is the middle, right? And that's the root locus. So that's the root locus, and here is here it's plotted. You know, that's it, right? So this is the plot. Know that this pole zero cancellation is presented here. But two branches would travel in this way, and then they would split off and go to infinity eventually. Now, what's interesting in the question, this question goes on to ask you other things. So it says here, so draw the root locus and calculate by hand the gain that ensures the dominant poles of the system have natural frequency omega n greater than 3 radians and damping ratio zeta greater than 0.7. So that's the part of the question. First, we needed to plot the root locus, right? We needed to plot it. And the second thing is, okay, we want to also find the values of the gain that achieves this. So this is done in the handout. So what are these two regions? Well, the maximum omega n greater than 3 radians per second would mean what? That we should be outside the circle of radius 3. But circle of radius 3, starting at the origin, right, would exactly pass through this point minus 3. It's the radius 3, right? That's it. And this slope of this line corresponds to the damping of 0.7. You can calculate that the angle between the imaginary axis and this line here should be arc sine inverse of 0.7. That's roughly 45 degrees, roughly, right? So this angle here, you know, is roughly 45 degrees. Also, this angle here is 45 degrees, it's symmetric. So now, the shaded region is where we should be to satisfy the specifications that you are given. Now, what's cool about this example, how it's chosen, is, by the way, you know, this pole zero cancellation, you will see, we are not at all worried about it because effect of the pole and zero are cancelled. So we are still talking about second order system as if there was no other, you know, poles, no zeros, right? So the interesting thing here is we satisfy omega n condition or rise time condition once we hit this point here, because after this gain, so suppose this is gain k1, as we keep increasing the gain, well, the branch of the root locus would be in this region. That's the shaded part. So note that initially this branch of the root locus is in the forbidden region. We are not satisfying what we want. As long as the gain is smaller than this critical value, we have one of the closed loop poles on this part. So we need to increase the gain sufficiently so that that branch, the pole corresponding to that branch, ends up here. And then we need to have a higher gain, but not higher than the gain corresponding to this point. Okay? So how would we now find the values of the gain so that in that region of gains, we are exactly in the shaded region? How would we do that? Which condition would we use? Magnitude condition. So what we need to do is, what is the gain corresponding to this point? I substitute minus 3, that's the point. The point on the root locus is minus 3, right? I substitute it into the transfer function, right? And I find this magnitude. Inverse of that is the gain. So you can calculate that this K minimum is 9.4. So that's the K minimum. You can calculate it that this breakaway point corresponds to the gain 9 over 4. That's done using the formula that I gave you, the magnitude condition. Now, how do we calculate the maximum gain corresponding to this point here? Well, we need to substitute this value of S into the transfer function, find the magnitude of that, and inverse of that would be the gain, max. So what is this point? Well, this angle here is 45 degrees. So basically, what would be the imaginary part of that point? It would be 3, plus minus 3. So this point here is really minus 3, that's the real part, and the imaginary part for this is plus J3, and here it's minus J3. And we need to find the value of gain corresponding to these points. So what we do, we substitute that into the transfer function. So what I did, S0 is now minus 3 plus minus J3. I substitute it and take 1 over magnitude of that. Well, that's exactly given here. So, and you get 18 over 4. So now what you got is the values. So in this case, you would satisfy your specifications to have the right overshoot and right maybe settling time if the gain is between these two values. See, we've done quite a bit of design here. We did quite a bit of design here. All right, so what I felt was important that you get a hang of simpler things, because sometimes we can get bogged down in calculations of various criteria, etc. Now, you have a number of solved examples in the worksheets. They are step-by-step explained. If you get stuck from any of them, talk to me. And I think you have now enough information on how to deal with general root loci. I will just show you an example. But by the way, piece of advice. When you are practicing these things, you construct all the features of the root locus. You put poles, asymptotes, parts of the line that belong to the root locus, breakaway points, intersection with the imaginary axis. You find all these features and you insert them into the complex plane. Now, how do you connect them? Now, what I advise is that you, using MATLAB, put a lot of root loci for different transfer functions. It's fun. Use complicated transfer functions with lots of zeros, lots of poles, different relative degrees. It's fun. You would see, it's a really great design tool. You quickly can see how proportional control affects your closed loop behavior. And I advise you, because if you see a lot of examples, you will form an intuition on how to connect the dots. Right? You have lots of features. The question is, how do I connect them? Well, see a lot of examples, and it's simple. In MATLAB, in half an hour, you can see 50 different examples. Right? Just root locus for this transfer function, root locus for that transfer function. Very easy, right? And use some really complicated ones. Go to, 5, 6 poles, 5, 6 zeros, different relative degrees. It would really help your intuition about how to plot these things. Also, in a data book, you would have tables of root locus transfer function and then root locus for it. So it's already done for you. There are some books that have, here's the transfer function, here's the root locus, transfer function, root locus, transfer function. It's like tables of Laplace transforms almost. It's useful to see lots of examples. Very useful to see lots of examples. Okay? And by the way, there are more complicated examples in the worksheet, they're step by step. So Ogata has lots of examples. I think you should be fine with all this. Are there any questions? All right, well, thank you. I'll see you next week then.
If this diagram is over here, let's say if gain is increased, can we say that it's stabilizing?
Well, but two branches would look like this.
Yeah.
They always stay in the right half plane, so you never stabilize the system.
But you said like
Yes?
it is part like dominant.
No. If you have unstable poles, nothing is dominant.
Okay.
Like you just have to. It's unstable.
Cool. And one more thing, when we use like 1 over magnitude of GS, is that this one?
Evaluate, yes. So G of S, and you just plug in S0. You get a complex number, and just take a magnitude of that
Yeah,
complex
I'm
number.
just confused. What's the transfer function for that part? Is that?
That's exactly the operator. That's this. That's this. Yeah.
Yeah. Okay. Thanks.
Yep.
For the root locus, if once we find the breakaway point, whatever it is for breakaway point, does that mean for any specific key, all the poles, whatever the asymptotic asymptotes would be, for a specific key, can I draw a circle and the intersect of the circle and the asymptotes would be where the root will be? Can I see that?
So you are asking where would other poles be located? Usually you would say, I want to get dominant poles, so they are symmetric. So if I know one of them, then the other one is just complex conjugate. But pick the dominant ones and determine what's the value of K for them. Other branches would then immediately give you some other locations of other poles. If you have 5 branches, I think you can, what I can do, I can say, all right, here are points, and I tell you already, all these 5 points correspond to the same thing. But often I can't do that. Often I say, well, pick K. Well, if I give you 5 branches, it's very hard to know what points on each branch corresponds to each value of K. So what I would normally do, I would say, all right, I want you to